This is a video for AQA Further Pure Mathematics. This is Matrices 2.1 Reflections in Two Dimensions. Firstly, let's consider the multiplication of the matrix 0, 1, 1, 0 and a column vector 3, negative 2. The answer to this, of course, is quite straightforward. It becomes negative 2, 3. What is of interest is if we consider the vector 3, negative 2 to be the position vector of a point at 3, negative 2 on the plane, then the product which results in negative 2, 3 we can consider as being the position vector of the image of that point under a transformation. So we say that the matrix maps 3, negative 2 onto negative 2, 3. So in general we can see that the matrix represents a reflection in the line y equals x. So we say it's a reflection in the line y is equal to x. And in this, a general point which is given by xy becomes a point which is yx. So in that particular transformation, the x and the y values swap round. If we have several points, perhaps representing a triangle ABC, then we can take the matrix for the column vectors or the position vectors of those points and multiply that by the transformation matrix. This again quite straightforward. We see that in fact what happens is that the bottom line then appears at the top, and what was originally on the top line becomes the bottom, so that the ABC maps onto a new matrix which represents the images of those points A, B, C. So we may refer to that as A dashed, B dashed, C dashed. Again, we can look at that in terms of a diagram. So here we have the original triangle ABC and its image A dashed, B dashed, C dashed. So we've seen then that in reflection in the line y equals x, a point xy goes to yx. The x and the y values swap round. So we could show that on a little diagram in this sort of fashion. For the line y equals minus x, then not only do they swap round, but they become negative, so that xy becomes negative y, negative x. And then on this diagram we can see that a point that was here at xy ends up over here at negative y, negative x. Now considering the reflections in the axes, first of all the x-axis, here the x value remains the same, the y value becomes negative of its original. So we can see that a point that was here at xy then transformed to a point down here with the same x coordinate but negative the y coordinate. In a similar fashion, the reflection in the y-axis, the x value becomes negative and the y value stays the same, so that a point here which was at xy is transformed over to here so that it is negative x, y. For any of the transformations you need to be able to determine the matrix that does the transformation, or conversely, given a matrix, determine what the transformation is that matrix is going to do. Now fortunately there's a way that we can do this quite straightforward, and it's referred to as the left hand rule. If you hold your left hand with the back of the hand facing you, then the thumb represents the vector 1, 0, and your first finger represents the vector 0, 1. These are what are called the unit vectors I and j. So I is the vector 1, 0, and j is the vector 0, 1. These are vectors of 1 unit long from the origin. The transformation matrix tells us where those vectors are going to end up when we do the transformation. So 1, 0 goes to 0, 1, and 0, 1 goes to 1, 0. So these are the images of I and j that we might refer to then as I dashed and j dashed. Now if you get the position of your hand into that, that shows us then we've ended up with a reflection in the line y equals x. Notice that if you're using this method, if you can see the back of your hand, then that will be a rotation, but in this case you can see the palm and we know it's a reflection. So the 4 reflection matrices that you need to be familiar with are given here. And rather than using your hand, it's very quick actually to just draw a quick diagram of where I and j have ended up. So remember that in the matrix, the first column is where I dashed is, and the second column is j dashed. So here we can see that I has remained where it was originally, and j has reflected down here, so we've got I dashed and j dashed, and that then is a reflection in the x-axis or the line y equals 0. The other thing which is worth remembering is that for all reflections, the determinant of the matrix will be equal to -1 for all of these reflections here. So we can calculate, for example, for the reflection in the line y equals x, remember that the determinant is produced by taking the product of the leading diagonal and subtracting the other product, and we see therefore we get 0 and -1. Well, if you want to do some more investigation about transformations and how we use the points 1, 0 and 0, 1 and their images, then you can do so using the following GeoGebra file. That's the end of this section, and in the next video we'll be looking at section 2.2, which considers rotations in 2 dimensions.